Humanity has always gazed at the stars, dreaming of venturing beyond our pale blue dot. From ancient civilizations mapping the constellations to modern astronomers using powerful telescopes, our fascination with the cosmos has been a constant. The night sky with its twinkling stars and the majestic Milky Way has always inspired us to look up and wonder about the possibilities that lie beyond. We envision reaching distant galaxies, encountering alien civilizations, and unlocking the mysteries of the universe. The idea of traveling through the vast expanse of space, visiting planets orbiting distant stars, and perhaps even finding life forms that are completely different from anything we know on Earth, fuels our imagination and drives our scientific endeavors. However, this dream of intergalactic travel faces numerous hurdles, and one of the most significant is deceleration. As we push the boundaries of space travel, we must confront the reality that reaching incredible speeds is only half the battle. The other half is figuring out how to slow down safely and efficiently when we approach our destination. While accelerating to speeds that make interstellar travel possible captures our imagination, we often overlook the crucial aspect of slowing down once we reach our destination. The technology and energy required to decelerate a spacecraft traveling at a significant fraction of the speed of light are immense and present a unique set of challenges. Imagine traveling at a significant fraction of the speed of light and then crashing into a planet or star. The consequences would be catastrophic, not just for the spacecraft and its crew but potentially for any life forms or ecosystems on the planet. This scenario underscores the importance of mastering deceleration techniques. Deceleration is not merely an afterthought, it is an equally daunting challenge that could make or break our intergalactic aspirations. Effective deceleration methods are crucial to ensure that we can safely arrive at our destinations, whether they are planets, moons, or space stations. The vast distances between stars demand incredible speeds for interstellar voyages. These distances are so immense that even traveling at the speed of light, it would take years to reach the nearest star systems. Therefore, achieving high speeds is essential for making interstellar travel feasible within a human lifetime. However, these same speeds pose a formidable challenge when it comes to stopping. The faster we travel, the more difficult it becomes to decelerate without causing damage to the spacecraft or its occupants. This is a critical issue that must be addressed if we are to make interstellar travel a reality. Just as a runaway train requires powerful brakes to halt its momentum, interstellar spacecraft need effective deceleration methods to avoid catastrophic consequences. The development of advanced braking systems, innovative propulsion technologies, and precise navigation techniques will be essential to ensure the safety and success of future interstellar missions. On Earth, friction helps us slow down. Whether it's the friction between our shoes and the ground or the air resistance against a moving car, we rely on this force to control our motion. However, the vast expanse of space is a near-perfect vacuum, largely devoid of matter to provide friction. This absence of friction presents a unique challenge for spacecraft. Without a medium to push against, traditional braking methods become ineffective. Imagine trying to stop a speeding car on an endless, frictionless ice rink. That's the challenge of decelerating in space. Moreover, the immense speeds required for intergalactic travel exacerbate the problem. To traverse the vast cosmic distances within a human lifetime, we need to achieve speeds that are a significant fraction of the speed of light. At such velocities, even a tiny amount of interstellar gas and dust can pose a threat, making deceleration a critical factor in the safety of the spacecraft and its crew. To understand the complexities of deceleration in space, we must delve into the fundamental principles of physics, particularly momentum and kinetic energy. These two concepts are crucial in explaining how objects move and interact in the vast expanse of space. Without a firm grasp of these principles, it would be nearly impossible to design effective methods for controlling the speed and direction of spacecraft. Momentum, often described as mass in motion, is a measure of an object's resistance to changes in its velocity. It is a vector quantity, meaning it has both magnitude and direction. This makes it a fundamental aspect of understanding how objects behave when forces are applied to them. The faster an object moves and the more massive it is, the greater its momentum. This relationship is crucial when considering the movement of large objects like spacecraft, which can travel at incredibly high speeds. The momentum of such objects must be carefully managed to ensure safe and efficient travel. Kinetic energy, on the other hand, is the energy possessed by an object due to its motion. It is a scalar quantity, meaning it only has magnitude and no direction. This energy is what allows objects to do work, such as moving other objects or generating heat through friction. Like momentum, kinetic energy is directly proportional to an object's mass and the square of its velocity. This means that even small increases in speed can result in significant increases in kinetic energy. Understanding this relationship is key to managing the energy of moving objects, especially in the context of space travel. This means that doubling the speed of an object quadruples its kinetic energy, making deceleration at high speeds even more challenging. Engineers must account for this exponential increase in energy when designing systems to slow down spacecraft. When a spacecraft travels at a significant fraction of the speed of light, it possesses an enormous amount of momentum and kinetic energy. This makes controlling its speed and direction a complex task that requires advanced technology and precise calculations. To slow down from such speeds, we need to find ways to reduce this momentum and dissipate this energy safely and efficiently, which presents a significant engineering challenge. Techniques such as using reverse thrusters, deploying drag devices, or even utilizing gravitational assists from other celestial bodies are all methods that can be employed. Each method has its own set of advantages and limitations, and often a combination of these techniques is used to achieve the desired deceleration. Section 4. Cosmic collisions, the danger of space debris. As we venture further into space, we must contend with the growing problem of space debris. These remnants of defunct satellites, spent rocket stages, and other fragments pose a significant hazard to all spacecraft, especially those traveling at high speeds. Even tiny particles, when impacting at a fraction of the speed of light, can cause significant damage. Imagine a grain of sand hitting a spacecraft at thousands of kilometers per second. The energy released in such a collision would be devastating. Decelerating spacecraft are particularly vulnerable to space debris collisions. As they reduce their speed, they spend more time exposed to the path of oncoming debris. This increased exposure highlights the need for advanced shielding, debris tracking systems, and potentially even active debris removal technologies to ensure the safety of future interstellar missions. Section 5. Putting on the brakes. Methods of deceleration in space. Given the challenges of decelerating in space, scientists and engineers have proposed several innovative methods to overcome this hurdle. Deceleration in the vacuum of space is a complex problem due to the lack of atmospheric drag and friction, which are commonly used on Earth to slow down vehicles. In space, we must rely on other forces and technologies to achieve the same effect. These methods range from utilizing existing technologies in novel ways to exploring entirely new concepts that push the boundaries of our understanding. Each method has its own set of advantages and challenges, and often, a combination of these techniques is required to achieve the desired deceleration. One promising approach is using magnetic sails, also known as mag sails. These devices leverage the natural forces present in space to create a decelerating effect without the need for traditional fuel. These large, superconducting loops generate a magnetic field that interacts with the charged particles in the solar wind, creating a force that can be used to both accelerate and decelerate a spacecraft. The concept is similar to how a sailboat uses wind to navigate the seas, but in this case, the wind is composed of charged particles emitted by the sun. Another method is reverse thrust, which involves reorienting the spacecraft's engines to fire in the opposite direction of travel. This technique is straightforward in principle but requires precise control and timing to be effective. This method requires a significant amount of fuel, especially for large spacecraft traveling at high speeds, making it a logistical challenge. The need for large fuel reserves can limit the payload capacity and increase the overall mission cost. However, advancements in propulsion systems like ion thrusters offer a more fuel-efficient option for long-duration missions. Ion thrusters work by accelerating ions using electric fields, providing a continuous and efficient thrust over long periods. Finally, we have the concept of gravitational slingshots, a technique that harnesses the gravitational pull of celestial bodies. This method has been used successfully in numerous space missions to gain speed, but it can also be used to slow down a spacecraft. By carefully maneuvering a spacecraft around a planet or star, we can use its gravity to alter the spacecraft's trajectory and speed, effectively stealing some of the celestial body's momentum. This technique requires precise navigation and timing to ensure the spacecraft follows the correct path. While this method is fuel efficient, it requires precise calculations and planning, as even a minor miscalculation could send the spacecraft off course or on a collision course. The complexity of these calculations increases with the number of celestial bodies involved, making it a challenging but rewarding method for deceleration in space. In practice, a combination of these methods is often used to achieve the desired deceleration. For instance, a spacecraft might use a gravitational slingshot to reduce its speed initially, followed by ion thrusters for fine-tuning its trajectory and speed. This hybrid approach allows for greater flexibility and efficiency in managing the spacecraft's velocity. As we continue to explore the cosmos, the development of advanced deceleration technologies will be crucial for the success of long-duration missions. These innovations will not only make space travel more efficient, but also safer for astronauts and equipment. The future of space exploration depends on our ability to master these deceleration techniques, enabling us to reach distant worlds and return safely. With continued research and innovation, we are on the brink of making these once theoretical concepts a reality.